All right, now we're going to move on to forces. So this is definitely the biggest unit in the course, and it's definitely what I think of personally when I think of mechanics. I always think of forces, Newton's laws. So to start, we're just going to introduce the concept of a force, which using that sort of elementary school type definition of just a force is a push or a pull, that's honestly not terrible. That's a pretty good intuition in what a force is. But of course, we have to be more precise here for AP. So we're saying that a force is an interaction between two objects that can influence motion. So a key here is that forces are between two objects. So an object cannot exert a force on itself. There must be two objects involved in any interaction. And additionally, any push or pull will be directed. So it makes sense that forces will be vector quantities, right? You can have a force to the right versus up. And our standard unit of force is a Newton. This is a derived slash defined unit because the SI unit for force would be a kilogram meter per second squared. And that's just kind of annoying to deal with writing every time. So we're actually going to start where it looks like we're going out of order because we lead with a principle known as Newton's third law. But this is really the most fundamental of all the principles for forces. And all Newton's third law says is that since forces are interactions between two objects, all forces will be paired, meaning anytime one object exerts a force on the other, that other object will in turn exert a force of equal magnitude but opposite direction on the original object. And there's no preference for which object is which in this case. So I think we'll just look at this with the picture. This makes the most sense. Um, for example, if I have a crate on the ground, the crate will be pushing down on the ground. But Newton's third law says that you can't just have one object exert a force on the other without this sort of reaction force. That's a common term you'll hear. Newton's third law is definitely described, especially at the lower levels, as like for every action, there's an equal and opposite reaction. Now, that's not the greatest phrasing of this, but you'll see that I talk about things in terms of action reaction pairs a lot due to my conceptual physics background. So, just so you're aware of what that means. So, for example, if the crate pushes down on the ground pushes up on the crate in turn. And those forces will have equal magnitude. So as soon as you see two objects interacting, you know absolutely there will be equal forces of opposite directions exerted on each object by the other. So this is why I claimed that an object can't exert a force on itself, because anytime an object does try to exert a force on itself, there will be that Newton's third law pair somewhere else in the system canceling the original force. So all this to say, forces are paired. We'll use this principle all the time. So, another really important quantity relating to forces is mass. And we're actually going to begin by talking about a force known as the weight force. We're going to take it as a fact that any two objects with mass will experience an attractive force towards each other, and that is just defined as the gravitational force. This is a type of mass known as gravitational mass, and this is the same sort of mass that you're probably thinking of, which is sometimes described as like the amount of stuff in an object, loose definition in chemistry. In physics, we define this inertial mass as a measure of how good an object is at resisting changes in its motion. So again, think about pushing an empty shopping cart versus a full shopping cart with the same force. The full shopping cart has a greater mass, thus it has a greater inertia, so it's going to move less or change its motion less under the same force. So that's all we mean. So this word inertia, it's it's just resistance to motion. So if you think about inertia as resistance, it's a pretty decent analogy there. And also, any massive object will generate this quantity called a gravitational field, which exerts forces on masses. Because we said that a force always requires two objects. And we are definitely feeling the Earth's gravity right now, and that's due to Earth's gravitational field. So our weight, our gravitational force exerted on us by the Earth, is from the Earth. So there's our other object. And when we deal with a quantity called a field, that's really just a map saying this is how strongly an object placed at this location would interact with the force. So in general, our force equation looks like some sort of quantity that the force is exerted on times this representative field strength. I included this for our E&M people later on. We'll see other equations take this form. But for mechanics, we only have this equation that says a gravitational force is exerted on masses. So that's why our formula says the gravitational force Fg is equal to the mass in kilograms times this gravitational field strength G. And notice this encodes the two object part of the force, right? Because your weight is determined by your mass as the person and the Earth's gravitational field. And also, we have seen G before. It turns out this G, this gravitational field, is the same G that we have been using in free fall. So we will discuss why this is when we talk about accelerated situations, but it does turn out that this gravitational field strength actually does represent an acceleration when you're in free fall. So the Earth is generating this gravitational field, which these units are actually equivalent to meters per second. But when dealing with forces, this value of G has a nice interpretation that it can be written as newtons per kilogram, which based on the formula, we can see that this says for every kilogram of mass you have, the Earth pulls you down towards its surface with 10 newtons of force. And this is generally what the gravitational field strength looks like at Earth's surface. It changes if you have big distances, but we will always assume we're doing our physics or we're close to the surface in these problems, unless if it's something about planetary motion. All right, that was pretty theoretical, so let's just do some problems now. Person of mass 60 kilograms is standing at rest on the ground at Earth's surface as shown. Calculate the gravitational force exerted on the person by Earth, including direction. So, when talking about forces, I'm not the most consistent at this, but I'll try to be. If I include the little vector symbol, then I am including direction. If I don't include the vector symbol, then we'll just be talking about magnitude. So, we said that the person has a mass of 60 kilograms, and I'll write it out with units just to show sort of what G actually means. And remember, the gravitational field strength near Earth's surface is just a constant. So we're saying that there's a constant gravitational field of 10 newtons per kilogram downwards, which is the same as 10 meters per second, but it's nice to write this as 10 newtons per kilogram. So we get the kilograms cancel, and the Earth is exerting a downward force of 600 newtons on the person. Okay, so we know that the Earth is definitely pulling the person down with 600 newtons. So what is the person doing to the Earth? Well, if we try to use the formula, it's going to become a problem because we'd have to find the mass of the Earth, which we definitely don't know, times the gravitational field strength that the person is generating. So that definitely is not our route to success here. But notice we just have this sort of like linguistic swap where we have force exerted on the person by Earth, on the Earth by the person. So anytime we just swap the order of which object is exerting the force versus receiving it, that's our key that it's actually Newton's third law, right? So we know for a fact that anytime two objects interact, the forces are equal in magnitude and opposite in direction. So the force on the earth by the person. And I'll show you just, I think I'll copy paste one because I'm lazy, and two to show you like what a Newton's third law swap looks like. So the force on the earth by the person will be equal to just the opposite of the force on the person by the earth. So if earth pulls down on the person pulls equally up on earth. So it wouldn't be 600 newtons down, it would be 600 newtons up. That should seem kind of odd that the person's actually pulling the earth up, but realize that in these situations, when the masses are so unequal, it doesn't matter that you're pulling on the earth. The earth has so much more mass or so much more inertia that it's not going to be affected by that force as much as the person is. So the causes are the same, but the effects won't. All right, now we are moving the person to the moon, where the gravitational field strength is 1/6 of Earth's gravitational field strength. So we're given that g of the moon is just 1/6 g on Earth's surface. So let's compare the mass of the person on the Earth versus the moon. This is a pretty common type question. So mass is inertia. It's how hard it is to accelerate you. Well, that's just based on the object itself. Doesn't matter where I am still equally difficult to accelerate. So mass, this is just a inherent property of the object itself, and it doesn't matter what their gravitational field strength is. Inertia is inertia. Resistance is resistance. But what is different is going to be the weight, because weight is a force between two objects. Because remember that weight is mg in magnitude. So I dropped the vector symbols. Well, we said that on the moon, there is a weaker gravitational field. So they will be pulled more strongly towards the ground on Earth versus the moon because there is a larger gravitational field strength on Earth. So weight represents how strongly a mass is interacting with a gravitational field. So since the gravitational field is stronger on Earth, the same mass will have a greater weight on Earth. Did I not ask you to calculate this? Their weight is 100 newtons. You just divide by 6. That's 6 times weaker. Interesting. I could have swore I had that. All right. Now we'll go with Newton's laws. Here is Newton's first law. So today, based on the section title, we're going to do all sorts of things with forces as long as they are balanced. So we will see that whether an object accelerates or not is determined on if there is a net force exerted on the object, and net in this class means what's the result when you add everything as vectors. You can also think of it as the winner or the winning force with direction. So we define the net force as the vector sum of all the forces, meaning ups and downs are going to subtract, lefts and rights are going to subtract, and so on. So Newton's first law says that an object will be in translational equilibrium, which means constant velocity, if and only if there is no net force on the object. So today's principle is this: an object moves at constant velocity if and only if all forces are balanced, meaning all forces on the object cancel. So there should be no result left or right. There should be no result up or down. This doesn't mean there are no forces. This means there's no net force. So if you have a down force, you must have an equal up force. If you have an up and right force, you must have a down and left force. So when we say write a Newton's first law equation, this is what we mean. We will sum up the rightward forces and set them equal to the leftward forces, because right and left must cancel out. And then we will set all of the upward forces equal to the downward forces, because all of the up poles must balance all of the down poles. Also, this is a special case, right? If an object is just staying at rest, it does have a constant velocity. It's a constant velocity of 0. So that's still Newton's first law. But also, this is the most counterintuitive part of Newton's first law for people, is that a moving object is possible to be in translational equilibrium because forces don't tell you about velocity. Forces tell you if the velocity is actively changing or not. So as soon as you see constant velocity, you know that forces balance. So net force determines the change in velocity, not velocity itself. So that means your ways to experience a net force would be speed up, slow down, change direction, because those are the ways to change your velocity vector. To model these, we will create what is called a free body diagram, or FBD. All of our objects are going to be modeled as dots, just to avoid having to create the actual diagrams. And we will just assume that an object is a point. And that's fine up until we start modeling objects with different parts that are rotating. That will come much later, but we can use the center of mass dot model for most things. So our rules for FBDs are that every force must be represented by an arrow that starts from the dot and points away from the dot. So we don't do tip to tail if there's multiple forces. We are just showing all forces that start from the dot and point away. So, for example, every single object on Earth ever will experience a downward force towards Earth's surface, mg, or fg. Sorry, we should use the actual labels. My notation is I like to use capital F for most things, and then a subscript. Everyone names them differently. I'm a fan of just name it with an F and a subscript. Now, if I had a different downward force, I would add it next to it and label that with the relevant force. The only force in mechanics that doesn't require active touching or contact is gravity. So if you're going to include a force that's not gravity on your free body diagram, make sure there is an active contact or touch happening. So it also should be pretty easy to determine where the force is coming from. So that's two reasons why velocity is not a force, because one, velocity is a property of a single object, and two, where is the velocity originating from, right? It would have to be coming from a different object, so that doesn't really make sense. And if I give you a grid, it means that we should be able to see some sort of balancing happening or non-balancing happening. So for example, we don't need to know what these forces are yet, but here's an example. This object is in equilibrium. So notice there's 4 forces. All of them are labeled. They're all distinct arrows that start on the dot and point away from the dot. And if we count our forces, we can see that the forces right would be 1, 1, 2, right? Because that angled arrow goes over 2. And then the leftward forces would be this right here. And that would also be 2. So it's balanced left and right, because there's 2 units of force in each direction. And then up, there's 2 units from the angled force. And then there's 1 unit from the just purely vertical force. So that would be 3. And then down would also be 3 units. So this is nice and balanced. Kind of be bad of me to give you a non-balanced diagram in the balanced section. Oh yeah, another thing. We don't actually draw force components. We rarely like the angled forces for analysis, but when drawing the free body, we have to keep it angled. So do not do this where we break this apart into this and this. Don't do that on your free body diagram. We have what I call like a component body that I sometimes draw for that, but do not draw it on the free body grid Only draw these forces. We're very particular in AP about how we do that. So we said there's a formula for the gravitational force or weight, mg. Not all forces have nice formulas. And we're going to talk about forces that specifically sort of change their value just to balance the scenario. So the first one, this is a force we're all familiar with, but probably don't know its name or even think about it, called the normal force, also known as the just surface force. Anytime an object is on a surface, gravity is attempting to push you through that surface. If I'm sitting in my chair, gravity is pushing me down. It would like me to go through my chair, through my floor, into the center of the earth. But that's not happening because there is a force exerted by my chair on me that cancels out that gravitational pull. And if I was heavier, the chair would have to push harder. So this normal force, this surface force, serves to balance that. That force always pushes directly out of the surface. It's not always up. If you have like angled surfaces, it'll change. If you have a vertical wall, it'll change. But a lot of cases, normal force will be vertically up because we're talking about the ground. And then another common balancing force would be tension, which is whenever an object is hanging from a rope or a chain. And we'll usually assume that our ropes and chains are ideal, meaning we pretend that they don't have any mass so that we can say there's uniform tension throughout. Now, if they do have mass, there will be more tension higher up because the rope will have to also pull up all of the rope below it. So this is an example of normal force, right? The Earth would love that it would love to pull that crate down through the center of the Earth, but that's not happening because there is a balancing force provided by the ground. And same thing here, the Earth would love to pull this crate towards the ground, but it's not going towards the ground because there's a rope pulling the crate. And we will assume that if our ropes are ideal, any single like continuous segment of rope, we'll assume it has the same tension everywhere. All right, we'll do the representative example of balancing forces now. So an elevator car of mass 500 kilograms is at rest on the ground as shown. Draw and label the forces exerted on the elevator car. Well, this elevator car is on Earth. So if it's on Earth, there's absolutely a gravitational force exerted on the car. But now, oh no, my elevator car is accelerating towards the center of the Earth faster and faster and faster. That means I need another force. So where could that force come from? Well, there's only two objects in this system. We have the elevator car and we have the ground / Earth. So there must be a balancing force provided by the ground. And of course, we have a nice special name for that. That's the normal force. Now, the grid shows that they're equal. You could go a step further and actually mark them with tick marks if you like that. I generally do that when I don't have a grid because I'm bad at drawing. So these are I don't care how bad I drew it. I am right. They are the same length because the marks tell you. All right, now it says, by writing an appropriate Newton's first law equation, calculate the normal force exerted on the elevator car. So a Newton's first law equation says that forces are balanced. There are a lot of ways that you can write this. I am a big fan of the left equals right, up equals down approach. So here, we just have vertical forces, so I just set the sum, bad sigma, the sum of the upward forces equal to the sum of the downward forces. The only force up is the normal force. The only force down is the gravitational force. And we can always find that gravitational force because it's just mg. So the normal force will just be mg, which is 500 kilograms times 10 newtons per kilogram. So the normal force must simply be 5,000 newtons to cancel the 5,000 newtons of downward pull provided by the Earth. All right, suppose instead we just lift the elevator off the ground but suspend it by a cable. Okay, well, elevator car is still on Earth. I should draw this the same as I did last time, not like the mass of the elevator car changed. So I'm drawing the same 2-tick FG. Okay, that's another thing. The actual like choices you use on your grid doesn't matter as long as you're consistent, because you're not given a numeric scale. All right. Um, but the elevator car definitely is not. It's not accelerating. It's suspended at rest. So we can once again say the forces are balanced, but it is not a normal force, because normal force comes from being in contact with surfaces. So only when there is a surface can I include normal force. So it must be something else. And what would that be? Well, of course, it's our second balancing force, tension, because it is hanging from a cable. All right, we can probably guess what's going to happen here. All that happened was tension is now serving the role that normal force did. So again, we can say that the sum of the upward forces is equal to the sum of the downward forces. The tension force up must balance the gravitational force down. So it's mg again, which is still 500 times 10, which is still 5,000 newtons. So notice the only difference is what force was supplying the balance. All right, here's a tricky one. Suppose instead the elevator is moving upwards at constant speed. Determine the tension in the cable. Justify your answer. So people usually think that, oh, it's moving, so it must be different. That's just not the case, right? We said the fundamental principle is constant velocity means forces are balanced. And in this case, it's not changing direction, so constant speed is constant velocity. So constant velocity means that forces balance. So doesn't matter if I'm at rest, moving up at constant speed, or moving down at constant speed. The tension in that elevator cable is going to be exactly 500 newtons again. So why were all these answers 5,000 newtons for the balancing force? We have at rest. So at rest means balanced. We have suspended at rest by a cable. At rest. Balanced. And we have constant speed, which means balanced, as long as you're not changing direction. So balanced means balanced and constant velocity are interchangeable. So do not think that moving requires extra force. You needed extra force to begin moving from rest, but to maintain that constant speed, no different than the amount to keep it at rest. All right, symbol math time. A block of mass 2m is suspended from a uniform rope of mass m and length L as shown. So this is a key here, is that the rope has mass. That is usually not the case. So we have to tell you if the rope has mass, and it does in this case. We want to rank the tension in the rope at points A, B, and C. And there's not a whole lot we can do here, so it must be a pretty straightforward ranking. So what is tension doing? Well, we see that the tension, it's definitely serving as a balancing force in this case. We see that the tension must balance the weight. Tension balances the weight below a given point. So if the rope was massless, the tension would be the same, because The rope at A's got to support the 2M, the rope at B's got to support the 2M, the rope at C's got to support the 2M. And there's no extra mass coming from the rope adding to the weight. But in this case, there is mass. So C has to support the 2M and a little bit of rope. B has to support the 2M and more rope. And A has to support the 2M and even more rope. So the tension is the least at C and the greatest at A because there's just more weight underneath the rope at A. And that's exactly what I said earlier, just formalized. All right, draw and label the forces exerted on the segment of rope below point B. So if we're being particular here, we have to name these forces a bit specially. But yeah, let's so what I'm gonna interpret this as, it's okay if we get a different free body diagram. It's fine if we disagree. I am personally going to interpret my own problem as saying, draw the forces exerted on this object. So I'm going to call this my object. I couldn't really figure out how to communicate that in the question. This is what I want. So like, consider this whole object as the thing we're drawing a force diagram for. So, well, we know that there's going to be gravitational force because there's a lot of mass there. So gravitational force. And of course, we're at rest. So a nice balancing, not normal force, but tension force. And also, this is just a good habit to get into. Next to your free body diagram, it could help to just write the Newton's first law equation next to it because you'll probably need it later. So like here, I can definitely see that Ft is equal to Fg. All right, here's a thing we can define that is usually helpful for these types of massive rope problems. We can define the mass per unit length, lambda, of the rope. So lambda is just defined as mass per unit length. And in the problem, we are just given that the rope has length m and length l. And that'll help us in part D. So derive an expression for the tension in the rope at a height y above the bottom of the string in terms of m, l, and y. So this was our setup. And we want to find the tension at a given height y. So we said earlier that the tension is just going to be the weight below a given spot in the string. So regardless of where we're at, we definitely have to balance Fg of the block. Are you a block or a crate? What are you? You're a block. Okay. And then we also have to balance Fg of the rope below a certain spot. So the Fg of the block is pretty easy. It's just 2mg. And then what is Fg of the rope below? Well, we know that we can write the amount of mass of the rope as the mass per unit length of the rope times how much length of the rope there is at that point. And we could see that because the length terms would actually cancel. Just showing that they're different here. So we said that mass per unit length was m divided by L. So we can write this as 2mg plus m over L times the length of the rope that we're dealing with, which in this case, we're not dealing with the whole rope, we're dealing with a height y times g. So this is definitely a bit of a interesting derivation going on here. But this is like the only problem I could think of asking with a rope that's not uniform. That's not ideal. And then using our expression from part D, determine the tension at the top of the rope. So what we just figured out is that the tension at a height y from the bottom of the rope is 2 mg plus m over L times y times g. So what would it mean to be at the top of the rope? Well, at the top of the rope, we would be a height L above the bottom. So we can find the tension at the top of the rope by plugging in L for y. The L's actually cancel, so I get 2 mg plus mg, which is 3 mg. And apparently this should be an expected result, it says. So why is this expected? Because the rope had total mass m. So if I'm all the way at the top of the rope, I have to balance the 2 mg from the block and the mg from the rope. So this is just the total weight. This is the total weight of this system. So we actually do expect that. All right, now we have some more fun with ropes. These are actually ideal. So what we can do whenever we have an ideal rope and ideal pulleys, we can say T is constant in a single segment. So in a single segment of rope, meaning there's just the same rope on both sides with nothing in between, we can just carry that tension through. And it is given to us that the objects are in equilibrium. So we want to rank the tension in each of these cases, and no justification because we're going to do it here. All right, so for A, find the tension where you can first. So we have a block of 2 kilograms. So we can definitely just say this is 20 newtons, right? Because we know that there's going to be a downward force of 20 newtons on this block. So there must be 20 newtons of tension up to cancel that. And now we can just do our property of an ideal string slash pulley, which means we can trace this 20 newtons all the way through a single string. So this is still the string, this is still the string, this is still the string, this is still the string. So actually everywhere it should be 20 newtons. So it's 20 newtons here, 20 newtons here, and it's also 20 newtons here. And we can see that that works because it should be 20 newtons because this force is also 20 newtons. So 20 newtons at A. Now if we look at B, actually should have put B first, I think. Easier to look at. We have 20 newtons up here to balance our 20 newtons down here. So this is 20 newtons again. And it should actually be stated that there's no net force actually on the string segment itself. This would just be the force pulling on adjacent segments. So there's 20 newtons pulling this way and this way. So maybe I should just denote it like that just to show you that there's no net force on the rope segment. So 20 newtons again. Then for C, 20 newtons. So you must be pulled up with 20 newtons. But now this is a different rope segment. Not that we asked about it, but actually up here, this would be 40 newtons because we have another block to balance. And then for D, being pulled down with 20 newtons. We're being pulled up here and here. So notice it can't be all 20 newtons here because that would mean there's 20 newtons here because it is the same string, and that's not balanced. So I'm connected to 2 strings, so I actually just need to half the effort. So it looks like the tension is the same at all points except D, where it is halved. So tension at D is less than a big tie at A, B, C. Because we said this was 10 newtons and these 3 were 20 newtons. So again, that's just how we tackle these ideal string situations, is a continuous segment of string, meaning it is all string. It is the same string. If you unwound it, tension will be the same throughout. So the only time it changed was because there was a break between this string and this string. That's why we got different tensions there. And here we just had two forces supplying the necessary balance, so it was half. All right. An object in equilibrium is subject to three forces. Two of the forces are shown, but the final force, F3, is not. Each grid line represents 1 Newton of force. So we want to draw F3. We want to determine F3 as a vector in unit vector notation, so component form. And then we got to calculate its magnitude. So we need to think about this in terms of balanced, because it says the object is in equilibrium. So we can just say that we have three forces. It's going to bother me that this is a bit unaligned here. We'll try to respace the two. All right, so we need, and then we're going to deal with like a net force column. Okay, so let's call you F1 and we'll call you F2. All right, F1, if I look at that, it says each grid unit represents 1 Newton of force. There'd be 1, 2, 3 forces in the left direction. That'd be -3. And it has 1 unit of force in the y, plus y. F2 has no horizontal component, and it has 1, 2, 3, 4, 5 in the down direction. So notice this is not balanced right now, because now the net force would be -3, comma, +4 for our forces. So what do we got to do to cancel that? Well, of course, we just need to reverse this, because if I'm currently -3 units too big in the x and +4 units too big in the, or -4, sorry, in the y, we just need to reverse this. So F3 must be +3 and +4. 3 and 4. Really need to get a new triangle. And we see the net force here would be 0 in each case. So that is our mystery force. So our mystery force must be 3 units right, 4 units up. So 1, 2, 3. 1, 2, 3, 4. And again, we can check that this works, because the horizontal forces will cancel, because this is 3. This is also 3. The vertical forces cancel, because this is 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5. So it all works out. So using unit vector notation, we can determine F3. Well, we already did. That's found in our table right here. So F3 as a vector would be +3 I hat, comma, +4 j hat. Or in unit vector, or sorry, with units here, this would be 3 newtons in the I hat direction plus 4 newtons in the j hat direction. Calculate the magnitude of F3. Well, magnitude of the force is, of course, going to be its hypotenuse. So if this is 3 newtons and this is 4 newtons, what could this possibly be for F3? Well, of course, Pythagorean theorem, square root, sum of the squares. It's a 3, 4, 5 triangle. You know how I operate. I operate making this as clean as possible, even if it means I have like 3 triangles in my library. So this is a nice little equilibrium. I feel like I've seen this on the test. I feel like I've seen this like exact question, like what's the magnitude of the result of the balancing force? It's back. Okay, so we have a crate that's resting on the ground. Resting crate. So this means balanced. Thank you. I've been doing that in purple. Bother me. Purple. Balanced. A resting crate is on the ground. There are 2 ropes attempting to pull the crate, but it is at rest, so nothing is happening. So, what are the forces exerted on the crate? Well, first of all, let's do the forces we definitely know are there. So, there will definitely be a gravitational force because the crate is on Earth. And it's always good to do the balancing forces last. So, balancing forces are normal and tension. So, more specifically, this force is the one that's fixed, and this is sort of a balancing tension. I do know that I'm going to have some sort of diagonal pulling force. We'll do maybe like this. It's usually good practice to make your FG pretty long because other things will work to balance that. So that's that FT. And now we got to deal with the balancing forces. So first of all, the balancing tension just needs to cancel out the rightward component of whatever I did here. Let's rename these. I'll rename these. We'll call this like T1 and T2. FT2, FT1. And then it's still not balanced because there's not enough up force. Right? There's 1, 2, 3 units of down force, and I have 1. Oh no, it is. I should probably make my G longer because we want it in contact with the ground. So I have 1, 2, 3, 4 units here, and I have 1, 2. Oh, it was fine originally. Let's keep it. It was fine originally. I just can't count. So my normal force is just going to be this little one to balance. So we can check that this works. Now, this isn't the only solution. As long as yours all balance out like this, it's fine. You should probably include a normal force, though. So we see here's an interesting case where, like, we have a balancing by committee, where the tension is kind of helping balance the gravitational force. So the normal force doesn't have to do its whole job like usual. But we can count here. So in the x direction, this was +2, so this was -2. In the y direction, we have +1, +2, +3. So we have -1, -2, -3. So it is all balanced. And this is sort of hard to look at. So what I create, I call this a component body diagram that I've made up, where you draw the object, and I usually just draw it not as a dot anymore, because this is not like an AP thing. This is like a U problem solving tool. So definitely the only force down is mg or FG. But now it's easier to see the balance if you break everything up into components. So the only thing we got to break is the tension force. So there's going to be an X tension from the first pull, and there is going to be a Y tension from the first pull. So this is why I call it a component body, because we have drawn the components exerted on the object. And why do I like the component body? Well, now it is really clear to write a Newton's first law sort of balancing scenario for this. So we can see that our two balancing equations would look like, we can definitely see these balance. So I know the x component of T1 must balance Ft2. And then I also know that the up forces must equal the down forces. So normal force plus the y component of the first tension must equal the gravitational force. So those are our Newton's law equations. A lot easier to figure out how to get those if you draw a component body. Normal force is not equal to the weight of the crate. Justify this claim referencing the forces drawn in part A. So I kind of spoiled this when we talked about it, but the component body makes this a lot easier to look at because we have a tension force that is helping out the normal force. So there's an additional upward force, meaning the crate, the ground doesn't have to push as hard on the crate as usual because it has gotten some help from that upwards push right here. So the fact that this pole is also angled up a little bit is the pulling force is upwards, so there's an upwards component on the crate from the rope. Thus, the weight is partially balanced by this Ft in the y direction. All right, let's calculate all the things. So we want to calculate everything. What are the horizontal and vertical components of the tension force from the angled rope? So we want Ft1x and Ft1y. So again, just like with projectiles, the angled stuff is always our starting point, but we're usually not interested in that. Components are so much more useful. So we are just going to break you down. This is my purple force. We're just going to break you down into components. And now notice this looks just like the projectile, like launch velocity. But again, the tried and true rule is that tack on a cosine to get the adjacent leg and tack on a sine to get the opposite leg. So this would be 50 cosine 37. Oh, I wonder what this will be. And this will be 50 sine of 37 degrees. So we have 50 cos 37 degrees and 50 sine of 37 degrees. And this is 345 again. Shameless 345 back to back, I guess. This would be 40 newtons and 30 newtons. All right, now we want to calculate the tension in the horizontal rope. So another reason we like the component body is you can start filling stuff in as you learn more info. So this was where we were at originally, but we just found the force components. So I can erase those. Do I want to erase them? No, I think I want to just say what they're equal to. We said this was 40 newtons and this was 30 newtons. So we can see just from balancing, the tension in the horizontal rope just has to balance that 40 newtons. So Ft2 is just going to balance the horizontal component of the tension of the pulling rope, which is 40 newtons as well. All right, now we're going to deal with the weight of the crate. This is the most free thing of all time because weight is just mg, and the crate, what are you, something nice? Oh, 10 kilograms, very nice. 10 kilograms, 10 newtons down for every kilogram, so 100 newtons of force. All right, so what's the normal force exerted on the crate? Welcome back, component body diagram. I am going to clean this up. So we have found basically everything. So we said this was 100 newtons. This was 40 newtons. This was 30 newtons. And this was 40 newtons. So our lone balancing friend would be the normal force. So we can see that the up force is equal to down forces. So the normal force plus the y component of the pulling tension diagonal must equal the weight. So normal force plus the 30 newtons of help we got from the rope must equal the 100 newtons down. So the normal force is 70 newtons, which is definitely not mg, less, as we thought. All right, simple math time. So now we have a hanging block. It is just symmetrically suspended by these two cables. We want to draw and label the forces exerted on this block. So there are two cables everything's symmetric, so this should be a very mirrored picture. So I'm just going to draw my weight. Just going to make it the whole thing. That's usually a good bet. And then the weight is being balanced by these two tensions. They are oriented at an angle. Doesn't matter what the angle is, we're just going to mirror them. So notice here that my mg was 1, 2, 3, 4 units long. So this means that each cable must be balancing half of that weight with its upward component. So as long as I do two cables with upward up 2, it's fine regardless of how I draw them. So I might do like, so see, we need to have 1, 2 units of upward tension in each of these cables. You could put it kind of anywhere on this line and it's fine, but I think it looks best here. And then we will do it symmetrically, like that. That doesn't look symmetric. I'm just going to freehand it. Not much better. We'll do the arrowhead last. Man, I'm just awful at drawing. This is a disaster class. We're going back to these. We're going back to these. I can't. I'm just going to do it better. Okay, there we go. Decent enough. This is FT. This is also FT. And we can see everything is balanced because 1, 2, 3 units right, 1, 2, 3 units left, cancel. 1, 2 units up, 1, 2 units up, 1, 2, 3, 4 units down. And I had to make them symmetric because this situation was symmetric. Make this a bit better. Tension in each cable is greater than mg over 2. Justify this claim referencing the forces drawn in part A. So why is that? So we're saying apparently the cable is more than half the weight in each of them. So why is that true? Well, we said here that half the weight must be given to the vertical component of each cable. So what that means is that there will be some extra force that's kind of doing nothing. So yes, the force we care about in each cable is mg over 2, but there's some extra wasted force that's the horizontal component, so we get some sort of hypotenuse, meaning the cable will have a greater force magnitude than mg over 2. So the vertical component each balances half the weights, but there's always also a horizontal component here, so the Pythagorean theorem gives us a greater than mg over 2. All right, what is the tension in each cable? And actually, this should have actually been my time to draw the component body. So we have gravitational force down. Then we have an upright tension. And they are the same. And then we have a left up tension. So that's why we can kind of do that reasoning. So yes, there are sort of two y tensions together must equal mg. So these are both going to be mg over 2. But there's this extra stuff on the horizontal that's going to create you a triangle. All right, what is the magnitude of the tension in each cable? Well, enter component body. Our component body tells us nothing interesting here. It just says tension equals tension. But the interesting one would be the sum of the up forces equals the sum of the down forces. Ty plus Ty equals mg. So 2 Ty equals mg. But we don't, Ty is not what we want. We want the actual tension in each cable. So, of course, we can just go here and break the tension apart. This would be ft cos theta, and this would be ft sine theta. And the vertical component is the one that we want, so we will replace fty with ft sine theta. So 2 times ft sine theta equals mg. So we can just divide everybody by 2 sine theta. So ft would be equal to mg divided by the quantity 2 sine theta. And we can do that because sine theta is a number, right? If I type in sine 30 in my calculator, I can press enter and get a number. So I can divide by sine theta. I can't divide by like sine, just like the letters, but I can divide by sine of something, right? That's just a number. All right, the hanging angle is increased and the block is still at rest. What happens to the tension? So we can analyze what that's going to do to our component body. So if we look at what happens if we have a much steeper hanging angle like this, what is that going to do? Well, that is going to change how these components are split up. So if I have a larger hanging angle, that is going to give more of my tension to the y than my x. So that means you get more hanging bang for your buck when we have more vertical, because we just said this tx, this is just wasted force. That's not doing anything. So we should just be looking for a large hanging angle so we can do it with less tension. So the new tension required is less because you get more bang for your buck distributed sort of in that upwards direction versus horizontally. So if the cable is increased, a larger fraction of tension is now vertical. So this means you get more vertical tension output for the same total tension input. So you just get a better deal out of it. How can we justify using part C? So we actually argued that, we derived that Ft was mg over 2 sine theta. So what are we doing? We're actually increasing the hanging angle. So m is the same, g is the same, 2 is the same. So we're increasing the hanging angle. So this is definitely a property that we need to know. Is that kind of what the trig function graphs look like on 0 to 90. So remember that cosine represents the adjacent component and sine represents the opposite component. So if we graph cosine theta and sine theta as a function of theta from 0 to 90, cosine theta, if theta is 0, it is perfectly horizontal, and if it's 90, it's vertical. So my horizontal component is going to decay like this, whereas sine theta is going to do the opposite. So all this is to say is that as theta increases, sine theta also increases because your cable is becoming more vertical. So as theta increases, mg over 2 sine theta is going to decrease because sine theta is in the denominator. I can definitely say that better. So as theta increases, sine theta increases, so ft is going to decrease because you're dividing by a bigger number. The sine of a bigger number in the denominator, you're going to be dividing by a bigger thing. That's our just basics of functional dependence, right? If you're in the denominator and you go up, the whole quantity goes down. So these are things to commit to memory, is that sine theta goes up with angle, cosine theta goes down with angle in the normal 0 to 90 range. Kind of tricky. All right, last one. This is just the letter version of the problem we did before, where we're pulling a crate with a given force. And we are going to be asked to compare the normal force on each block and do some symbol math. All right, so the only thing that is different is going to be the angle of the pull. So it's usually good practice just to make your G long enough. Now we'll do 3. I like 3. 3 is going to work for this. All right. Now, the pull will be the same. So I'm going to do the same pulling force, just orient it differently. So the vertical and horizontal components will be the same. It's just one of them is up and one of them is down. So I think it's pretty reasonable to do like, let's do 2 and 2. 1 and 2. So that's an FT, and then 2 and 2. That'll be an FT. Let's move my FG end. All right, then we'll do my balancing forces. So my tension, my other tension here, well, I have 2 units right, so I need 2 units left. And same here. And then for my normal force, you know what? Don't bother me. I've been making normal force a different color than this, so you're going to be purple. So then we have to just deal with normal force. Again, I always like to do normal force last because I know it's a balancing force. All right, so for the first one, I have 1, 2 units up and 1, 2, 3 units down. So I need an extra unit up. Here I have 1, 2, 3 units down and 1, 2 units down. So I need 1, 2, 3, 4, 5 units up. That's kind of interesting. So if we were to component body each of these, we'd see that we have FG down for this one. We have FT1X here. We have FT1Y here. Then we have FT2 here. And then we have FN here. And now just changing a couple things, we see the only difference between the two will be that the up pole component gets turned into a down pole component. So this would be our component body diagram. All right, what's happening to the normal force in each scenario? Well, this is actually easy for us because we know the answer definitively because we drew this correct. This was 1 unit and this was 5. So, and we drew the pulling forces and the G's the same, so we know we can accurately compare these. So it's definitely bigger in the second scenario. And why is that? Well, notice in the first scenario, this is what we had in the original problem from before, where this tension was helping the normal force balance gravity, so it didn't need to be as big as mg. But in this case, we actually are fighting gravity with a downward pulling component, so the normal force has to exert a larger force than usual. So here, the normal force is less than mg because it's getting help, and here, the normal force has to be larger than mg because it's being opposed. And I misspelled crate. Lovely. We have an upward component of the pulling force, so less than mg in scenario 1. We have a downward pulling force, so greater than mg normal force in scenario 2. All right, let's figure out what Fn1 is. So, balancing time. we're just going to set the upward forces equal to the downward forces because that is what Newton's first law is all about. We have a component diagram. Component diagram for scenario 1 says there's two forces up, Fn and Fty. And together they must balance mg. We don't know Fn, but we can figure out Ft1y because it says this force is just F. And it's just our usual trig. It's just our favorite little triangle rule where this is cos and this is sine. So F sine theta equals mg. So Fn would just be mg minus F sine theta. And that should make sense because we can interpret this formula as saying the normal force needs to push back with the weight of the crate minus whatever help it got from the pulling. So that's why that's our results. Now it says using your expression for Fn1, determine Fn2. Oh yeah, this is 1. We should be using the notation. Well, it says determine, and that usually means it's just a very simple thing, or we could just kind of look at it. So Fn1 needs to push back with mg minus whatever help it got. So Fn2, well, that's going to be slightly different because it needs to push back not just with Fg, but with whatever component was working against the normal. So it's just a sign swap here, right? Because the second normal force would just be mg plus the extra pushing it has to do due to the downward component of the force. And okay, we're done. Wow. A lot of stuff there. Yeah, force balancing is a pretty deep topic. So that aligns us with sort of our basics of Newton's first law.